Hello everyone and welcome to the video on natural log functions and differentiation. This will be really the first video of our second semester, so we are on our way. We're getting close to completing everything we need to cover. And like I said in class, we should be able to get everything done right now at least before spring break. So for the video today, the objectives. Number one, develop and use properties of natural log functions. Number two, understand the definition of the number e. And the third thing is find derivatives of functions involving the natural log function. So this one is really going to be looking back at some things we've done recently as well as some things that we did last year. So hopefully you're feeling comfortable with some of the recent stuff, and when we look at the old stuff, that you say, oh yes, I do remember that. Let's start out by changing our definition of the natural log function. Last year we had a definition that we worked. It was really what allowed us to go and alternate from exponential notation to log notation. We used the definition we had to rewrite every log as an exponential, or to rewrite exponentials as logs. This one is what we're going to do is actually more formally define it. In terms of how, where the function actually comes from. The natural log function is defined by the natural log of x is equal to the integral from 1 to x of 1 over t dt. X must be greater than 0. So this is why the domain of a natural log is all positive reals. So the first thing I would like you to do is I would like you to copy down this chart here. And you'll notice that for x I have 1/2, 2, 3, and 9. And so what I would like you to do is verify that the natural log of each of these is equal to the definite integral from 1 to x of 1 over t dt. So you can go through on this one. All you have to do is take your calculator out and put in natural log 1/2. You'll get your answer. What I'd like you to do here is, in this part, is use the numerical differentiation feature on your calculator, or numerical integration feature. That's Math 9 on your calculator, and write down, in each case, write down as many decimal places as you possibly can. So that should, that should go through and convince you that this function up here is actually equal to the natural log function. So pause the video now and do these 8 calculations. Welcome back. You can see that I've done these calculations as well. In blue, we have the natural log function, the values of the natural log of each one of these, and you'll notice that in red we have the values of that definite integral. And you'll notice that they do match up. The natural log of 1/2 is the same thing as the integral from 1 to 1/2 of 1 over t dt. And the natural log of 9 is the same as the integral from 1 to 9 of 1 over t dt. So you should go through and be comfortable with the fact that this is actually equal to the natural log function. Also, you'll notice if you look at this, you can see that there are some of the properties that one of the properties you're familiar with the log was the idea of the exponent moving down in front. And you'll notice that 1/2, another way of thinking about 1/2 is that 1/2 is 2 to the negative 1 power. And you'll notice that it shouldn't surprise you then that the natural log of 1/2 and the natural log of 2 are just opposites of each other. So we could go through, and that would be, by using this 2 to the negative 1, that would be negative 1 times the natural log of 2. Same thing with 9 and 3. We know that 9 is equal to 3 to the second power. And therefore, if we know the natural log of 3 to the second power, if you remember again, one of the rules that we used last year was bringing that exponent out in front. We'd have 2 times the natural log of 3. Well, if you notice, if you take 2 times the 1.098612289, you will get what you see for the natural log of 9. Now, how does this definition help us out? Well, what we're going to do is I want you right now to recall this version of the fundamental theorem of calculus. The idea that if I take the derivative with respect to x of the integral from a to x of f of t dt, that will come out to be f of x. Now when we look at the natural log, we've defined the natural log as equal to this definite integral, the integral from 1 to x of 1 over t dt, again where x is greater than 0. So what I can do is just take the derivative of both sides. So I now have the derivative of the natural log of x equals the derivative of the integral from 1 to x of 1 over t dt. Well, by applying this fundamental version of the fundamental theorem of calculus, I know that this integral here is actually equal to 1 over x. And so therefore, I know that the derivative of the natural log of x is equal to 1 over x. We can also take the second derivative then. The second derivative would be of the natural log of x would be actually just be the derivative of this. And so we know the second derivative of the natural log of x comes out to be negative 1 over x squared. Now, a couple other things I want you to keep in mind. Again, remember, x is greater than 0. So this tells us a couple different things. Number one, the derivative of the natural log of x, 1 over x, is always going to be positive. It's always going to be positive. So that tells us that graphically, the natural log function is always increasing. So this portion there, it's always going to be greater than 0. So ln of x is always increasing. The next thing we know is, again, because x is greater than 0, our second derivative is negative 1 over x squared. Well, I know that will always be less than 0 because we're going to put positive numbers in for x. We're squaring a positive number, which is going to be positive, and we got that negative sign, this negative sign just sitting out there. So I know this is always going to be less than 0, and so therefore, I know that graphically, the natural log of x is going to be concave down. So what I know on this is I know this thing is always increasing, and I know it's concave down. And since it's always increasing, I also know it's 1 to 1. And if you think back about that last year, that was something that was important as well because of the whole inverse aspect of it. So we know this thing is increasing, we know it's concave down, and we know it's 1 to 1. So looking back, some properties of the natural log that you should be familiar with. The domain of the natural log is going to be from 0 to infinity, all positive real numbers. And the range is all real numbers, so it's going to be anything from negative infinity to infinity. As we mentioned, the function is going to be continuous, increasing, and 1 to 1. And the graph is also going to be concave down. Now here's some log properties that you should remember as well. We spent a lot of time last year looking at these. So to start out with, we're going to assume that a and b are going to be positive numbers and n is going to be irrational. Then the following properties are true. First up, the natural log of 1 is equal to 0. Now think about that definition that you know. Right now, we know that the natural log of x is the integral from 1 to x of 1 over t dt. Well, looking at that, when we put 1 in for x, I'm getting the integral from 1 to 1 of 1 over t dt. Well, that gives me 0. So it makes sense that that would be 0. Also, we have the second one that we have is the natural log of a times b is going to be the natural log of a plus the natural log of b. Remember how we break that up? 3 was a property we were talking about a little earlier, the idea that this exponent can be brought out in front. And then kind of the opposite of property 2, the natural log of a over b equals the natural log of a minus the natural log of b. Now you're going to want to make sure you are comfortable with all of these properties right there. You want to make sure you're ready to go with those because we're going to be using those quite a bit in these problems. And the last thing we want to do is just more formally state what is going to be true as you work with these things. One, we've talked about already that the derivative of the natural log of x is 1 over x, and that again is x greater than 0. And when I have the derivative with respect to x of the natural log of u, so we're kind of getting the chain rule, it's going to be 1 over u times the derivative of u with respect to x, which is also u prime. So we can think of that as u prime over u. this will come into play at times to help us out as we're working on these things, as well as some of the log properties. So now let's go ahead and take a look at a couple examples. Let's look at the first example that we have is that we want to find the derivative of the natural log of 5x. Well, what happens with this one? We go through, we're going to look at the property that we just talked about, that the derivative with respect to x of the natural log of u is going to be equal to u prime over u. So in this case, for our problem that we're looking at here, I can say that u would equal 5x, and then u prime is going to be 5. So the derivative with respect to x of the natural log of 5x comes out to equal 5 u prime over u, which is 5x, and when you reduce it, it's 1 over x. Our second one that we have that still can use this same property. In this case, I could say u equals x squared plus 3x. So u prime is going to be the derivative of u, which is going to be 2x plus 3. And therefore, I can say then that the derivative with respect to x of the natural log of x squared plus 3x is equal to u prime 2x plus 3 over u, x squared plus 3x. That would be the derivative of that natural log function. Now it's your turn. What I want you to do is I want you to pause the video and find the derivative with respect to x of the natural log of sine x. So now I'm throwing in a trig function here. So go ahead, pause that video, use this same idea here to come up with the derivative of the natural log of sine x. Welcome back. You should have come up with that the derivative of the natural log of sine x comes out to be cosine x over sine x, or as we also are familiar with on this one, that is equal to the cotangent of x. Now let's take a look at a couple other examples here. These ones are going to be a little bit more complicated in terms of the derivative because of the types of functions you're working with. So let's look at number 3. I want to find the derivative with respect to x of x times the natural log of x. Well, in this problem, you'll notice that I am dealing with a product. I have a natural log in there, so I got to work with that, but it is a product. And so I know that when I take that derivative there, that it is going to end up being the derivative of the first, which is going to be 1 times the second, which is the natural log of x, plus the first, x, times the derivative of the second, which is going to be 1 over x. And so when I simplify that, 1 times the natural log of x, I get natural log of x, plus x times 1 over x is 1. So I know the derivative with respect to x of x times the natural log of x comes out to be ln x plus 1. Now also, let's take a look at number 4 here. Now, very often, I see this happen a lot, that people will look at this and say, wait a second, we did those log properties, and I know that exponent can be brought out in front. And you might be thinking the same thing. The issue we have here is this. You can only pull that exponent out in front when the exponent is being applied to what's inside the natural log function. In this case, that exponent is actually being applied to the natural log function itself. And so since it's not on the thing that's inside, it's not on just the x, I cannot use the property that, the log property that we just looked at, where we could bring the exponent out in front. So what do I have to do in this one? Well, I just have to use the chain rule. I'm starting out, I'm taking the derivative of something to the 4th power. And so I know when I take the derivative of something to the 4th, that's going to be 4 times that something, in this case the ln of x, to the 3rd power. Again, remember, it's because you don't change that what's inside function, times the derivative of what's inside. Well, I take the derivative of natural log, and so I get 1 over x. So the end result on this is equal to 4 times the natural log of x to the third power, the whole thing over x. That would be the derivative of the natural log of x, the whole thing raised to the fourth power. The next function I want to find the derivative of is the natural log of the x squared times the square root of x minus 5. Now in this situation, you might be looking at this saying, wait a second, we dealt with things like this before where we took the derivative of the natural log of u was u prime over u. Well, I'm looking at this problem here, and the u prime is going to be kind of complicated to work with. And it's going to be a lot of extra work, and I don't want to deal with that. So what I'm going to do to help myself out on this one, to find that derivative, is I'm going to go through and use the log properties to break this up. So right now, when I look at this, I have the we'll deal with the derivative aspect later, but I know that I have the natural log of x squared times the square root of x minus 5. And I know by the log properties that when I'm with the multiplication, that's going to be the natural log of x squared plus the natural log of the square root of x minus 5. Which that's the natural log of x squared plus the natural log of x minus 5 to the 1/2 power. And now, since at this point, since these exponents here just apply to what's inside the log, I can now use that property. And I can say this is equal to 2 times the natural log of x plus 1/2 times the natural log of x minus 5. And so what I'm actually going to do when I'm trying to answer this problem is I'm taking the derivative with respect to x of that natural log of x squared times the square root of x minus 5 is really just going to be the derivative with respect to x of 2 ln x plus 1/2 ln of x minus 5. And I can go on this one and say, well, I know the derivative of natural log of x is 1 over x, so that's going to be this first part right here. This part is just going to be 2 over x plus 1/2 times the derivative of natural log of x minus 5 is 1 over x minus 5, or I'll get 2 over x plus 1 over 2 times the quantity of x minus 5. Now you can distribute the 2 in that denominator, and you could also go and get a common denominator, but at this point this really is sufficient, and I would say that would be our correct derivative for this particular problem. Now what we're going to look at is logarithmic differentiation. Now, logarithmic differentiation is a technique that we can use to go and find the derivative of functions that are fairly complicated. Now what we're looking at here is one that's not super bad. You have dealt with problems and you've taken derivatives of things much more complicated than y equals the square root of x plus 3 over x squared plus 1. But I want to use this one to illustrate this process and how this works. Now, I will ask you in your assignment to do logarithmic differentiation. It is a valid way of taking the derivative of any function, okay? At the same time, I want you to realize that logarithmic differentiation is not a technique that you have to do on the AP exam. The reason I'm showing it to you, though, is that this is a technique that will help us derive some of the other differentiation rules that we're going to be working with in the near future. So we're going to start out with y equals the square root of x plus 3 over x squared plus 1. So what I'm going to do with logarithmic differentiation, the very first thing you do is just take the natural log of both sides. So if this is true, then I can say the natural log of y equals the natural log of the square root of x plus 3 over x squared plus 1. Just took the natural log. And now I'm going to use my log properties to break this up. So I know that that's going to be the natural log of the square root of x plus 3 minus the natural log of x squared plus 1. And then the natural log of y, bringing down the exponent, is going to be 1/2 ln of x plus 3 minus the natural log of x squared plus 1. Again, at this point, now some of you might be looking at that saying, wait a second, can't I take this 2 and bring it out in front? And again, the answer on that is no. The reason you can't is that 2 only applies to the x. It's not being applied to the 1. So if that 2 had actually been sitting right out here, then I could pull it out in front. But the way it's written right now, I cannot do that. So now at this point, we have gone and taken, we've used the log properties. We took the natural log of y, and we used the log properties to break this up and to get it down, make it as simple for us as we possibly can. And now what I'm going to do is I'm going to use implicit differentiation. So I know that the derivative, remember, derivative of the natural log of u with respect to x was u prime over u. Well, when I'm taking the derivative of the natural log of y, I know that that is going to be y prime over y, and that's going to equal 1/2 times 1 over x plus 3 or minus, well, the derivative of the natural log of x squared plus 1 is going to be u, which is u prime, which is going to be 2x over x squared plus 1. So what I have right now is y prime over y equals 1 over 2 times x plus 3 minus 2x over x squared plus 1. And what they want us to do now is to solve. Remember, we're trying to find y prime. We don't want to know what y prime over y is. We want the derivative of that function right there. So the derivative of that is going to be y prime. So to find y prime, I'm just going to go back to this, and I'm multiplying both sides by y. And so I can say now that y prime is going to be 1 over 2 times x plus 3 minus 2x over x squared plus 1 times y. Or the fact that we can just say that y prime is equal to 1 over 2 times x plus 3 minus 2x over x squared plus 1. That thing times the square root of x plus 3 over x squared plus 1. And that would then be the derivative of that particular function. Now you could go through, multiply this thing out, and you'd see it all work out to be what you would get with that. But that is the process that we have for logarithmic differentiation. And you will be asked to do this process for some of the problems that we're working with. Lastly, let's just look at the definition for E, which again is Euler's number. And that we know that the letter E is going to be the positive real number such that the natural log of E is going to equal the integral from 1 to e of 1 over t dt, and that comes out to equal 1. So it's the value that will make the natural log equal to 1. And so that's where this number, where it was developed from. And some other things that we know, if you look back to what we had before, you'll notice where we were at the beginning when I asked you to make that table. You'll know that the natural log of 2 happened to be less than 1, and the natural log of 3 happened to be greater than 1. And so it makes sense that the natural log of E has got to be something between 2 and 3. And what we have is Euler's number, which is the number 2.718, blah, 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 continuing on forever. So this concludes our video on natural logs and the differentiation there. A lot of what we're going to be doing in class is going to be taking derivatives of functions that involving natural logs, but keep in mind, don't forget the rules that you know so far as well. The idea of the product rule, the chain rule, the quotient rule, all those things still come into play. Also, the derivative of the different trig functions and the power rule will also come into play as well. So with that, I hope you have a good evening, and we'll see you in our next class.